Hello GATE aspirants, welcome to GATE Chemical Solution channel. This is 2 mark fluid mechanics question in the year 2021 GATE question paper. Please read the question very carefully and identify what is given and what you have to find out. We will see the concept for this problem, then we will go for the solution. So all of you well aware of this diagram, right? This is nothing but the shear stress versus velocity gradient plot at the constant temperature and pressure. This is given for different fluids. The curve indicates the behavior of Newtonian fluids for shear stress versus velocity gradient profile. Okay, the curve will be straight line passing through the origin. Okay, it means the shear stress is directly proportional to the velocity gradient. The proportionality constant is indicated as viscosity. So the relation is given, all of you know, that is tau xy equal to minus mu into du by dx, right? So this curve, the next the Bingham plastic curve, the examples are mentioned here, we will see later. The Bingham plastics, we have to apply certain stress for the flow of such fluids are called as the Bingham plastic fluids. So it means minimum stress is applied, then only the fluid start to flow. The examples will be toothpaste, the ketchup, we have to, some stress will be applied, right? Then if you press, then only the toothpaste is coming out, right? So that's why this is called as the Bingham plastic fluids. The stress applied to flow is called as the yield stress. So once the flow starts, it will be again straight line. So that is the direct relations will be there, similar to the Newtonian fluids. So when we will see the pseudoplastic fluids, it at low shear rate, it is a concave downwards. Increasing shear rate, again it will be a straight line. Okay, so these are called as the shear rate thinning fluids. It means with increasing shear rate, the viscosity of these pseudoplastics will be decreasing. Okay, inversely proportional viscosity and shear rate for pseudoplastics. Whereas in dilatants, the curve D indicates the dilatants, it is concave upward at low shear and constant at high shear rate. Okay, clear? So it is concave upwards at low shears and straight line at high shear rates. Okay, these are called as the shear rate thickening fluids. It means with increasing the shear rate, the viscosity of dilatant fluids will be increasing. Okay, so examples of these fluids is given here for Newtonian fluids, gases, water, and most of the liquid hydrocarbons, organic liquids of the low molecular weight comes under Newtonian fluids. So the Bingham plastics will be toothpaste, ketchup, sewage sludge. When we will see the pseudoplastics, that is pseudoplastics are called as shear rate thinning. So it means viscosity will be decreasing with increasing the shine rate or shear rate. The examples are the most polymer melts, rubber latex and polymer melts. Here polymer solutions. Rubber latex and polymer melts. So when it comes to the dilatants, shear rate, it is thickening. Shear rate thickening fluids, that is viscosity increases with increasing the strain rate. That examples are quicksand, cornstarch suspension in water and some sand filled emulsions. The relations, the viscosity and shear rate relations will be given for each fluid. For Newtonian fluids, this is like this. For Bingham plastics, this is the yield stress. Again, it will be a relation will be Newtonian fluid relation. Okay. So for pseudoplastics, This is k prime into du by dy power n prime. This k prime is called as the flow consistency index. This is called as the flow behavior index n prime. For pseudoplastics, n prime should be less than 1. For dilatants, the same relation, n prime should be greater than 1. Okay, these relations are sometimes called as the at a certain region of viscosities and behavior. These are called as the power law fluid relations or Ostwald-Vivaldi relations also we can call it as. Okay, clear? Now we will see the solution for this problem. So in the experiment 1, the shear stress is applied 2 Newton per meter square. The plates are separated by a distance 1 mm and the velocity, the top plate is moving with a velocity of 2 meter per second. Okay. See, in this experiment 2, the plates are separated by a distance 0.25 mm and shear stress is applied as 3 Newton per meter square. Here velocity, the top plate is moving with a velocity of 1 meter per second. So they have asked us to calculate what is the rheological character of the fluid, what is the type of fluid, what it means, what is the behavior of the fluid. So initially first we will calculate in viscosity in both the cases, then we will see what is the behavior. From Newton's law of viscosity, this is the relation, right? So we know the shear stress is given and velocity is given, the separation between the plates is given, so we have to find out the viscosity in both the cases. In the experiment 1, du by dx1 equal to 2 minus 0 divided by 1 minus 0 into 10 to the power of minus in terms of meters, we will get 2 into 10 to the power of minus 10 cube second inverse. From this, viscosity 1 equal to, in experiment 1, viscosity 1 equal to tau y x1 divided by du by dx1, that equal to 2 by 2 into 10 to the power of 3, that equal to 10 to the power of minus 3 Pascal second. Viscosity in the experiment 1. In viscosity in the, first we will calculate the shear rate du by dx at the second experiment, 1 minus 0 divided by 0.25 minus 0 into 10 to the power of minus 3 equal to 4 into 10 to the power of 10 cubed second inverse. From this, viscosity 2 equal to tau y x2 divided by du by dx of 2, that equal to 3 by 4 into 10 cube. From this, 0.75 into 10 to the power of minus 3 Pascal second. So if you observe these values, here the shear rate is, the experiment 1 shear rate is 2 into 10 to the power of 3, here shear rate is 4 into 10 to the power of 3. So here from experiment 1 to experiment 2, the shear rate is increasing, whereas what about the viscosity? Viscosity here 1 into 10 to the power of minus 3, here 0.75 into 10 to the power of minus 3. It means with increasing the shear rate, what happens, the viscosity is decreasing. It means it is a shear rate thinning fluids, right? So which fluids follow this behavior? That is nothing but the pseudoplastics. Okay, clear? For Newtonian fluids it is constant, viscosity should be constant for Newtonian fluids, but this is not the case. So option A is not is the correct answer. Option A is not correct answer, right? If you look at the option B, so shear rate is, this is the correct answer, right? Pseudoplastics for shear rate thinning fluids. So for dilatants also not the correct answer. For this, viscosity should be increase with increasing shear rate for dilatants. So this is wrong option. So ideal and inviscous means viscosity should be 0 for ideal fluids. So this is also not the correct answer. Okay, clear? So if you like the video, please share and give your valuable comment in the comment section. Thank you.